Hello students, in this session we are going to discuss magnetic effects of electric current, that is electromagnetism. The concept of electromagnetism first explained by Danish scientist Ørsted. In this session we are going to discuss concept of electromagnetism, terms relating to electromagnetism, different field patterns, direction of magnetic field, work law, BIOT SAVARTS law and their applications. Ørsted experiment. Whenever a current is passed through a conductor, a magnetic field is created around the conductor. This field is called electromagnetic field, and the direction of magnetic field depends upon the direction of current. He observed this phenomena by placing a magnetic needle near the current carrying conductor. Let us consider a conductor carrying current and place a magnetic compass near the conductor. We observe the deflection of magnetic compass in a definite line or path and in a definite direction. These lines are called magnetic lines of force, which indicates the force of attraction of the magnet. We also observe that the line of force points towards the magnet at one end and away from the magnet at the other end. The end of the magnet from which the compass needle points is called north pole and the other end is called south pole. This can be seen from the two figures shown. Here this indicates the north pole from which the line is flowing, and this indicates the south pole from which the line of flux is terminating. Now we can define line of force. It is the path or line which gives direction of force experienced in the magnetic field. Now we will see the properties of lines of force. Magnetic lines of force are continuous. They always form closed loops. That means they originate at one place and close at the same place. They never cross one another. They starts at north pole and finishes at south pole. They pass through all materials, both magnetic and non-magnetic. For example, all magnetic materials like aluminum, nickel, cobalt, and non-magnetic materials like air, wood, rubber, etc. And lines of force behave like elastic bands. They are imaginary lines of force, that means they are not visible. Now the definition of magnetic field is the region or space around a magnet in which the imaginary magnetic lines of force exist and in which its effects can be seen is called magnetic field. Now we will define magnetic flux. The total number of magnetic lines of force in a magnetic field is called magnetic flux. It is represented by symbol phi. It is measured in Weber. Generally 1 Weber is equal to 10 power 8 lines of force. The definition of magnetic flux density. The flux per unit area terminating at right angles to the surface of magnetic flux is called flux density. It is denoted by symbol B and its units are Tesla, that is indicated by T, and it is in SI units. Flux density B is given by phi by A, where phi is the magnetic flux and A is the area of cross section in meter square. Permeability. The ability of a medium to permit magnetic lines of force is called permeability. It is denoted by symbol mu. Its units are Henry per meter. Now we can define magnetic field strength or magnetic field intensity or magnetic field strength. Field strength at any point in a magnetic field is the force experienced by a unit north pole placed in the magnetic field. It is represented by H and is measured in Newton per Weber or Ampere per meter. Now we will see the direction of magnetic field produced by flow of electric current, and it is given by two rules named Maxwell's corkscrew rule and right hand thumb rule. Now we shall examine the Maxwell's corkscrew rule. Suppose if a corkscrew is imagined to move bodily in the direction of flow of current just shown in the figure, then the direction of rotation of the screw gives the direction of magnetic field, that is in clockwise or anti-clockwise. Now we will consider the two cases of Maxwell's corkscrew rule. Suppose when the direction of bodily motion of the screw, which indicates the direction of current, is away from the observer or inwards, which is generally represented by a cross or plus, then the direction of rotation of the screw, which is clockwise, indicates the direction of magnetic field that we can see from the figure shown. That is, if current is away from the observer, that is indicated by a cross, then rotation of the corkscrew is away from us or inwards, then the direction of magnetic field is clockwise. Now we will consider the second case, that is when the current is outwards or towards the observer, which is indicated by a dot, then the direction of rotation of the screw is anti-clockwise. Therefore, the direction of magnetic field is in anti-clockwise direction. Now we can explain the second rule for the direction of magnetic field, that is right hand thumb rule. This is stated as follows. Imagine that the observer holds the current carrying conductor in the right hand with thumb pointing the direction of flow of current. Then the fingers curling around the conductor points the direction of magnetic field around it. Now we consider the first case of right hand thumb rule. If the direction of current is upwards, which is indicated by thumb, the fingers curling in anti-clockwise direction indicates the direction of magnetic field. Let us see the figure shown. Here the thumb is pointing upwards, which gives the direction of current. Then fingers curling in anti-clockwise direction gives the direction of magnetic field. We will see the other case, that is, if the direction of current is downwards, which is indicated by the thumb in the figure shown, then the fingers curling in clockwise direction indicates the direction of magnetic field. Now we will see the field patterns of different considerations. Now if we observe the field pattern of straight current carrying conductor, the field direction is a set of concentric circles around the axis of conductor, and the direction of the concentric circles, that is clockwise or anti-clockwise, is depends upon the direction of current, that is either towards the observer or away from the observer. Now we will see the field pattern of solenoid. First of all, a solenoid is defined as, it is generally a hollow cylindrical tube having number of turns wound helically along the length of the conductor, and these turns are generally insulated from hollow cylinder, and coils are closely wound. Now we can see the field pattern of solenoid from the figure shown. Here the direction of field is always from north pole to south pole, and both ends forms north pole and south pole of the solenoid. Next we will see the field pattern of toroid. A toroid is a steel ring in which a magnetic circuit is entirely within the ring, and there is no external magnetic field. That means it is a closed steel ring and the field direction is continuous inside the steel ring. A toroid cannot produce any poles. We will see the work law, which is used to find field strength of different patterns. It states that the net work done on or by a unit north pole, that is UNP, of magnetic field strength 1 Weber, in moving once round any single closed path in a magnetic field, is numerically equal to the product of current I and number of turns enclosed by the path. It can be explained from this figure. If the UNP, that is unit north pole, having a pole strength of 1 Weber, is moved around the n conductors carrying a current of I ampere in paths A and B as shown, then work is to be done. If we consider path C, which is also a closed path, but work done is 0, since it does not link any current carrying conductor. Now, if we say mathematically, the work law closed integral of H r dr is equal to N I, where H r is the magnetizing force at a distance of r meters from the conductor. N is equal to number of conductors enclosed by the closed path. I is equal to current flowing through the conductors. Now, we will see the applications of work law. Work law is used to find the magnetizing force H of a long straight current carrying conductor and a solenoid. Now, we will see the field strength due to a long current carrying conductor applying work law. Let us consider a long straight current carrying conductor and a unit north pole of pole strength 1 Weber. Suppose that a unit north pole is placed at a distance of r meters from the center of the conductor. If the UNP is moved once round the conductor against the field strength produced by the straight current carrying conductor, then work done by the UNP is equal to force into distance, where work done by the UNP is given by the product of force into distance. Here the force done by the unit north pole is called field strength and it is denoted by H, and the total distance travelled by the UNP is equal to the perimeter of the circle. Therefore, work done is given by H multiplied with the perimeter, that is 2 pi r. Here the ampere turns enclosed or linked by unit north pole is equal to N into I, but here the number of turns is equal to 1 since it is a long straight current carrying conductor. Therefore, according to work law, the total work done is equal to number of ampere turns. Therefore, work done, that is H into 2 pi r is equal to I, or it can be written as H is equal to I by 2 pi r ampere turns per meter. Suppose there are n conductors enclosed by the unit north pole, then H is equal to N I by 2 pi r ampere turns per meter. Now, we will apply the work law to calculate the field strength on the axis of the solenoid. Let us consider a solenoid of a length of L meters and consider a closed path at which a unit north pole is placed and it is moving in the closed path as shown. Then the total work done by the unit north pole in the given path is equal to force multiplied with total distance travelled, and here the total distance enclosed by the path is only equal to L, because here there are two paths in the magnetic path. One is solenoid iron path and second one is the path through the air. Here the flux enclosed by the air path is equal to almost 0. Therefore, we could not consider this path, and because the field strength or magnetic field is stronger in the iron path when compared to air path, therefore, we will consider the length in the closed path is equal to L. According to work law, work done is equal to force into distance. Here the force is nothing but the force experienced by the unit north pole, which is indicated by the field strength, that is H, multiplied with the total effective distance, that is here only L meters, because H outside the solenoid is small when compared inside, and the number of ampere turns linked by the UNP is equal to Ni, where N is the number of turns enclosed by the solenoid and I is the current flowing through the solenoid. Therefore, according to work law, work done, that is H into L, is equal to number of ampere turns Ni. In other words, H is equal to Ni by L ampere turns per meter. Therefore, the field strength on the axis of the solenoid is given by H is equal to Ni by L. Now, we will see the other law, that is LAPLACE'S law or BIOT-SAVARTS law, to find the field strength of a differential length dl at a distance of r meters at a point P. It states that the force dF or the field strength dH experienced by a point pole of pole strength m Weber at a point P of r meter distant from current carrying conductor of length dl meter is given as dF or dH is equal to mi dl sin phi by 4 pi r square, where I is equal to the current through the differential element of the conductor dl, and phi is equal to angle between the direction of current along the conductor, that is of differential length dl, to the direction of r from conductor to point P. Now, we will see the other law, that is LAPLACE'S law or BIOT-SAVARTS law, to find the field strength of a differential length dl at a distance of r meters at a point P. It states that the force dF or the field strength dH experienced by a point pole of pole strength m Weber at a point P of r meter distant from current carrying conductor of length dl meter is given as df or dh is equal to mi dl sin phi by 4 pi r square, where I is equal to the current through the differential element of the conductor dl, and phi is equal to angle between the direction of current along the conductor, that is of differential length dl, to the direction of r from conductor to point P. Okay. Now we will derive an expression for field strength on the axis of a circular coil. Let us consider a single turn coil carrying a current of I ampere. The field strength or magnetizing force due to a small element dl at point P on the axis of circle at a distance of x meters from center of the coil, as given by the Laplace law, dh is equal to I dl by 4 pi r square plus x square. Here r square plus x square is the distance between differential element dl and the point P at which field strength to be derived. Here the direction of dh, that is field strength at point P, is at right angles to the line PQ. Therefore, the dh can be resolved into two components, that is dh1 and dh2. Here dh1 is equal to dh sin theta, which is axial component, and dh2 is equal to dh cos theta, that is equal to vertical component. The vertical component dh2 at point P due to the element dl at Q is cancelled by due to the element dl at point M on the circle. The same thing applies to all other diametrically opposite pairs of differential lengths dl around the coil. Therefore, the resultant magnetic field strength at point P will be equal to sum of the axial components only, that is total field strength H is equal to sigma dh1, that is sum of axial components, which is equal to sigma dh sin theta. Therefore, that is equal to I dl by 4 pi r square plus x square sin theta, since dh is equal to I dl by 4 pi into r square plus x square. Therefore, that is equal to sigma I dl by 4 pi r square plus x square multiplied with r by root over r square plus x square, since sin theta in the given circle is r by r square plus x square under root. Therefore, that is equal to sigma I r dl by 4 pi r square plus x square whole to the power of 3 by 2. It can be written as sigma IR by 4 pi r square plus x square whole power 3 by 2 into closed integral of dl from 0 to 360 degrees. Here closed integral of 0 to 360 degrees dl is considered to calculate the total length of the circle. Since the total length of the circle is equal to 2 pi r, this expression will be equal to sigma IR by 4 pi r square plus x square whole to the power of 3 by 2. Rearranging this equation in the form of sigma IR square by 2 into r square plus x square whole to the power of 3 by 2 into r by r. Therefore, it will be equal to I by 2 r into r cube by r square plus x square whole to the power of 3 by 2. Here r cube by r square plus x square whole to the power of 3 by 2 is equivalent to r by root r square plus x square whole cube, which is equal to sin cube theta. Therefore, equation for field strength H is equal to I by 2 r multiplied with sin cube theta ampere turns per meter. If the circular coil consisting of n turns, then total field strength H will be Ni by 2 r sin cube theta ampere turns per meter. So far we have discussed Oersted experiment, definitions of magnetic field, flux, flux density, field intensity and permeability. We have seen field patterns of straight conductor, solenoid and toroid. We have discussed about Maxwell's corkscrew rule and right hand thumb rule. We have also seen different field patterns. We have derived expressions for field strength using work law and BIOT SAVARTS law. In the next session, we will discuss some more topics. Goodbye.
Further clarification, contact the Additional Secretary, State Board of Technical Education and Training, 7th floor, BRKR Bhavan, Tank Bund Road, Hyderabad 500063. Fax 040 322 0546.